Hi, this is TW Huang. Today I'm going to talk about composable tasking in Taskflow. This is a very useful feature in Taskflow to help you handle large parallel problems. This is the takeaway for today's presentation. First, we will understand the importance of task graph composition and learn how to compose task graph in Taskflow. Then I will showcase two real-world examples of task graph composition and conclude the talk. The main idea of task graph composition is very simple. Instead of designing one giant monolithic task graph, we build complex computations by composing many small task graphs. You can think of this as building Lego blocks. Rather than handcrafted sculptures, each block is small, well-defined, and easy to combine with others. Task graph composition gives us several important advantages. First, we can expose parallelism at multiple levels. Both inside and outside compose subgraphs. Second, it gives us a modular interface. Each piece is easier to test, verify, and reason about. Third, we get reusable building blocks, such as algorithmic patterns and primitives that we can reuse in different applications. Why is task graph composition important? From the productivity's perspective, developers can reason about small graphs instead of massive one, which facilitates faster design, testing, and iteration. Composition also makes collaboration easier when dealing with large parallel problems. Different people can work on different components without stepping on each other, which enables clean interface and ownership between boundaries. More importantly, task graph compositions let you separate what computation does from how it is integrated. This allows independent design, reuse, and faster evolution of each component. Although task graph composition is important in many aspects, it is unfortunately not well supported by existing tools. In other words, most existing task parallel programming libraries assume a flat task graph structure. They can only handle a single flat task graph at once with no notion of reuse. As a result, existing libraries often fail to scale to very large and complex parallel problems. For example, on the lower left, in OpenMP tasking, you cannot treat each task as a reusable task that can compose other tasks or graphs. Similarly, in TBB, you can create nodes and edges but cannot encapsulate a task graph as a reusable object. In summary, existing libraries do not really support composable task graphs, forcing us into a flattened design that is very difficult to reuse and scale. Now, I'm going to show you how Taskflow overcomes this challenge and study how to program composable tasking. Task graph composition in Taskflow is mainly supported by a special kind of task that we call a module task. A module task is created by calling a function composed of from a Taskflow to encapsulate a Taskflow graph. Once created, the module task can be used just like other tasks to build dependencies. For example, here I have two task flows, F1 and F2. F1 has three tasks, F1A, F1B, and F1C, and F1C runs after F1A and F1B. On the other hand, F2 has four tasks, F2A, F2B, F2C, and a module task that encapsulates Taskflow F1. So, when we run F2, the scheduler will start with F2A and F2B. When they finish, the scheduler will run Taskflow F1, F1A and F1B and then F1C. Finally, the scheduler goes back to Taskflow F2 and run F2C. As you can see, composable tasking in Taskflow is very clean and easy to understand. It is important to understand that a module task does not own its task graph, but only keeps a reference to the task graph it encapsulates. This is basically the same as executor that does not retain any ownership over a running task flow. Therefore, it is your responsibility to ensure that a composed graph remains alive throughout its execution, so you don't encounter invalid references or program crashes, and remains exclusive during its execution, so you can prevent data race on the encapsulated graph. For example, on the lower left, we have two modular tasks that encapsulate the same task flow and run one after another. This is valid because the two executions are sequential. However, on the lower right, the execution is invalid because the two modular tasks may run in parallel, which can cause data race on the same encapsulated task flow. A modular task can recursively encapsulate graphs, so you can implement hierarchical task parallelism in a very natural way. For example, here I have a task flow F4 that consists of two sequential modular tasks. Module of F3 runs before module of F2. Inside module of F2, we have three tasks, F2B, F2A, and F2C. And another modular task, module of F1, that goes recursively to another two tasks, F1A and F1B. Similarly, inside the module task, module of F3, we have one task F3A and another modular task that encapsulates the task flow F2 we just talked about. As you can see, the composable tasking interface in Taskflow can naturally express this hierarchical task parallelism. Instead of creating a modular task from a task flow, you can use the standalone function tf_make_module_task to create a modular task from a task flow. Semantically, there is no difference between the use of compose_of and make_module_task. They are equivalent to each other. For example, in the code below, I can either use compose_of to create a module task that encapsulates F1 and F2, or in place the task returned from the function tf_make_module_task on F1. The two implementations achieve exactly the same behavior. One thing that makes tf_make_module_task special is that it can work with asynchronous tasking, so you can launch a modular task asynchronously. For example, here I have four task flows, A, B, C, and D, each with a single task that prints its task flow's identity. Then I use the function tf_make_module_task to create four modular tasks and assign each to an asynchronous execution. As you can see, these four task flows are executed asynchronously without creating another task flow to encapsulate them. Similarly, tf_make_module_task can work with dynamic task graph parallelism, where you can launch modular tasks asynchronously and create dependencies on the fly. For example, here I have four task flows, A, B, C, and D, each with a single task that prints its task flow's identity. Then I use the function tf_make_module_task to create four modular tasks and assign each to a dependent async task, which enforces a linear execution order on A, B, C, and D. Now, I'm going to show you two real-world examples where task graph composition can really help. The first example that can benefit from task graph composition is data processing workflow, which is very typical in today's machine learning and AI-driven applications. The workflow typically consists of three stages to process a dataset: feature extraction, data analytics algorithm, and post-process the result. You know, feature extraction can be a parallel algorithm that transforms raw data into meaningful numerical or categorical features. Once feature is extracted, we can apply parallel data analytics algorithms such as clustering, classification, or regression to classify the data. Finally, we refine, visualize, or summarize the results depending on the application need. And these three stages are not just different tasks, they are different parallel algorithms. So, instead of mixing all logic into one large, flat task graph, we can compose three task graphs, each specialized for one stage, so the overall program is easier to test, debug, and optimize. This slide shows an example code that implements the data processing workflow. We have three task flows that implement the three stages of the data processing workflow: feature extraction, clustering, and post-processing, and one top-level task flow to encapsulate the three task flows in a single graph called workflow. The key point here is each stage is implemented as its own task flow, so the implementation and integration are modular, self-contained, and focus on a single responsibility. Then, the executor will run a composed workflow graph correctly, orchestrating the parallelism both inside and outside the three modular tasks efficiently. The next example that can benefit from composable tasking is building algorithm primitives. You can create a task graph that implements a specific algorithm and expose it as a modular task. And I'm going to use the pipeline algorithm as an example. So, what is the pipeline parallelism? Pipeline parallelism refers to a parallel execution of multiple data tokens through a linear chain of stages or pipes. Each stage processes one data token sent from the previous stage, applies the given callable to that data token, and then sends the result to the next stage. And the parallelism occurs when multiple tokens are processed simultaneously across different stages. For example, here I'm showing you a 3-stage pipeline that processes 4 tokens in 4 parallel lines. On the right-hand side is the flattened task graph, where the maximum parallelism happens on the diagonal direction. When the first token moves to pipe 2, the second token can move to pipe 1, and the third token can start in pipe 0. That is the pipeline parallelism. You can build a task parallel pipeline in Taskflow using TF pipeline, which is a composable graph for implementing pipeline parallelism. Here, what you need to write is really just the algorithm interface. You describe how many parallel lines you want, and then you define each pipeline stage using the pipe object. For example, in the first stage, we process tokens one by one, and we stop after 4 tokens have been processed. Once the pipeline is defined, you simply compose it into a task flow, give it a name, and run it with the executor. The important point here is that you are designing the pipeline at a very high level. All the scheduling, synchronization, and execution details are handled automatically by the modular task underneath. If you are interested in learning more details about the pipeline feature in Taskflow, please check out the link below. In today's presentation, we have understood the importance of task graph composition and learned how to program task graph composition in Taskflow. Finally, we showcase 2 real-world examples that can benefit from task graph composition. If you are interested in learning more about Taskflow, please check out our project website at taskflow.github.io. You can post your questions on the issue page of our GitHub repository. With that, I'm going to stop here. Thank you very much.